Okay, so we had started talking about the theory of gravity. It's this amazing uh, discovery that was made a few hundred years ago, that every object in the universe exerts an attractive force on every other object in the universe. So you have two particles here with masses m1 and m2 separated by some distance r. Each one of them will exert an attractive force on the other. The magnitude of it is given by this. G here is gravitational constant. It's about 6.67 times 10 to the minus 11. And then you have the product of the two masses, m1 times m2, divided by the distance between them squared. And the key thing here is that m1 is exerting the same force on m2 that m2 is exerting on m1. It's just that their directions are opposite. M1 is pulling m2 towards it, and m2 is pulling m1 towards it. So this is the magnitude and the direction. This is the gravitational constant. I'll just do a quick recap of some of the things that we had considered in the last class. So remember, in the last class, we derived from first principles this idea that all objects fall towards the Earth with a universal acceleration of 9.8 meters per second squared. And that follows as a direct consequence of Newton's law of gravitation. So let me write that over here again. So remember, the Newton's law of force of gravity is given by G, m1, m2 over the distance between the two objects squared. That's the magnitude. So let's apply this principle to the force that is exerted on some mass m that is very near the surface of the Earth. So maybe it's like 1 meter above the surface, or maybe it's 10 meters above the surface. Then this r, the distance between the two objects, is between the center of the Earth and the center of this object. That's the distance. So obviously it's the radius of the Earth plus whatever extra 1 meter or 10 meters we're talking about. But if you're really close to the Earth, like just 1 meter above the ground, then the radius of the Earth plus 1 meter is basically the radius of the Earth, right? So we can kind of ignore. So in this limit here, we can just say that r is essentially approximately the same as the radius of the Earth. So then in this situation, the force experienced by the mass m is given by the gravitational constant times the product of the masses, so it's the mass of the Earth times the mass of the object, divided by the distance between them squared, which is approximately the radius of the Earth squared. So this is kind of a more detailed picture of that. This is the mass m just above the surface of the Earth. It's experiencing a net force, the force of gravity acting on it. It's the only force acting on it in free fall. And that has to equal the mass times the acceleration by Newton's second law, right? Newton's second law, remember, says that the net force on an object is equal to its mass times acceleration. So in this case, let's choose the positive y direction to be downward. Then this is a force in the positive direction. So it'll come with a plus sign, and that's going to equal the mass times the acceleration. Right, so the F net here is the force of gravity, and that is equal to the mass times the acceleration of the object. And so if I then solve for the acceleration, because remember, we're trying to show that all objects fall with the same acceleration, then essentially the m on both sides cancels out, and you're left with the idea that this acceleration is just g times the mass of the Earth over the radius of the Earth squared. And we give these collection of constants here, we give it the symbol g. And if you go to Wikipedia and look up the numbers and plug them in here, you will find that this is 9.80 meters per second squared. And because the mass canceled out on the left and the right, it didn't matter what the mass of this object was, whether it's 5 kilograms or 100 kilograms, it doesn't matter. The acceleration is completely determined by g, the mass of the Earth, and the radius of the Earth. So therefore, all objects fall towards the Earth at exactly the same rate, 9.8 meters per second squared. Okay. And if you were to repeat this analysis on the surface of the moon, then all that's going to happen is that the acceleration will be a new value of g, which will involve the mass of the moon and the radius of the moon instead of the Earth. So if you again go to Wikipedia, look up these numbers, you will find that g on the surface of the moon is 1.62 meters per second squared. So it's a smaller acceleration near the surface of the moon. Any questions on that? All right, so that's sort of the recap of what we did in the last class. And then we introduced the idea of weight. And so we use the word weight in colloquially all the time. But in physics, again, it has a very precise meaning. The meaning of the weight of an object on some planet is literally the value of the gravitational force that is acting on the object due to the planet. That is the meaning of weight. So your weight on Earth is equal to, in newtons, the force, the gravitational force that the Earth is exerting on you. Okay. And again, the gravitational force has this form right here, g times the product of the masses over the distance between them squared. So the force that you are experiencing due to the Earth is g times the mass of the Earth times your mass divided by the radius of the Earth squared. So this is your weight. And of course, this thing here in brackets is just the g, the 9.8 meters per second squared. So when you're near the surface of the Earth, we will say that your weight is m times g, where again, g is really derived from properties of the Earth. So this m times g, your mass times 9.8 meters per second squared, is the gravitational force that the Earth is exerting on you. So keep in mind that there is a difference between your weight and your mass. Your mass is this m, right, like 100 kilograms, but your weight is 100 kilograms times 9.8 meters per second squared. And that's in units of newtons, in SI units. In the US customary units, force is in units of pounds. And so therefore, when you say someone weighs 150 pounds, that's actually the gravitational force that is acting on them, expressed in US customary units. Yes?
You said that someone's mass was whatever kilograms. So how would you find your mass? Like if you, because you couldn't stand on the scale because that's your weight.
That's correct. So in fact, that is a good question. How would I find the mass? If you know the weight, that's what your scale is telling you. If you divide that by g, that's going to give you your mass in kilograms. Any questions on that? And again, this is your weight on the surface of the moon, where the g is now 1.62 meters per second squared instead of 9.8. And you can also figure out what is your weight on the surface of the sun. G there is insane. It's 274 meters per second squared. Because remember here, this G sun, you get by doing gravitational constant times the mass of the sun over the radius of the sun squared. That number comes out to be 274 meters per second squared. So an object that has the same that has a given mass will have a different weight on different planets, even though it has the same mass. Any questions on that? So absorb this concept. Take a minute, stare at the screen. We're gonna try and do a few questions on this. So keep in mind that there's going to be a question on top hat about something happening on the surface of the moon. Keep in mind that g on the surface of the Earth is 9.8 meters per second squared. On the surface of the moon, it is 1.62 meters per second squared. The weight of an object is m times g on the surface of that planet. And the mass of the object is the weight divided by the g on that particular planet. So here's a question. Where it says, which costs more? This will be a top hat question. So which costs more, 1 Newton of gold on Earth or 1 Newton of gold on the moon? So, say it again. That is a good question. So yeah, so let's take out the societal component of that. The more gold stuff you have, the more it's going to cost. That means mass, right? And so what we're being told is not the mass of, this is kind of like when you're 90 and people are just hanging out in space, it's common, you might get a scammer trying to sell you 1 Newton of gold from the moon or from the Earth or some other planet, and you have to make sure that you understand what is being sold to you. And so the question is, which costs more, a Newton of gold on Earth or a Newton of gold on the moon? Okay, so if you're given two options, you can either buy 1 Newton of gold as measured on Earth or 1 Newton of gold as measured on the moon. Which one of these options will cost you more? And again, the more stuff there is for the gold, the more it's going to cost you. So again, think about this equation here. The weight is equal to m times g. What you're being given right now is the weight. And let's go to top hat. Okay, so here's the question. All right, 5 seconds. All right, it's all over the place. Anyone want to defend their answer? Did you say no? It's okay. Anyone on Zoom? I'll just stand here uncomfortably, awkwardly. Yes, go ahead.
It's the same value because they're both newtons.
Right.
They have the same amount of gold.
So is Newton equal to weight or mass? What is a unit? Is a, well, Newton is, so let me correct you there. The Newton is a unit of force, right? and weight is a force. Your weight is the force that the planet is exerting on you. So yeah, so you have the right idea, but you have to keep in mind that the thing we're after is the mass. The more mass something has, the more it's going to cost because there's more stuff with it. And so what we're being told here is, let me just go ahead and say the correct answer is indeed C. Because, let me go back here. Because what we're told is that the weight, which is equal to mg, let's say that this is 1 Newton. So therefore, we're told that 1 Newton is equal to m times g. And so therefore, the mass of the object will be its weight of 1 Newton divided by g. And so now you have two options. In one case, you're told it weighs 1 Newton on the surface of the Earth. So on Earth, the mass will be 1 Newton divided by g on the Earth. And for the moon, the mass, the weight is the same, 1 Newton, but divided by g on the moon. And so this is 1 Newton over 9.80 meters per second squared. And this is 1 Newton divided by 1.62 meters per second squared. And so you see that if you are told something has a weight of 1 Newton, yeah, go ahead.
Well, if we were to get a mass, we would have to say it's mass. Because kilograms.
Right.
We would have to say.
Well, what in this problem, they're telling you that on any given planet, you can always trade in weight for mass because it's just a factor of g, right? So on any given planet, weight and mass are related to each other up to this factor of g that is specific to that planet.
Yeah.
So
Trying to figure out if it was a mass, probably have to say. Like the mass of this is what? On Earth, is it the same on the moon?
right,
I would have to say mass.
correct. The mass of any object is the same no matter where it is. The mass is just literally the number of atoms that are in it, right? So it's the mass. It has nothing to do with what planet it's on. But the weight does depend on where it is. An object with the same mass will have different weights on different planets.
If it said like, it said kilograms, would that weight or would that be mass? Or does that say mass?
If it says kilograms, then that is mass, right? So Newton is a unit of force. Weight is a force. It is literally the gravitational force acting on you. And kilograms is a unit of mass, and that's the amount of stuff. So yeah, if this problem said, which costs more, let's say it said 5 kilograms of gold on Earth versus 5 kilograms of gold on the moon, in that case, what would the answer be? It would be equal, that's right. It'll be B, because it's 5 kilograms. You're selling me a gold with some number of gold atoms. So it is what it is, and that's the price, it doesn't matter. But if you're telling me that something, you're giving me the weight of 1 Newton on Earth, versus 1 Newton on the moon, that corresponds to a different amount of mass on the two planets, right? So on the moon, the gravitational G is smaller, so you need more mass for it to have the same weight as compared to on Earth. Any questions on that? Okay. Here's another top hat question. This is sort of a numerical question, so get out your calculators. We'll go to top hat in a second. it says calculate. So we just showed this, uh, we just answered this question, and we found that 1 Newton of gold on the moon uh, costs more than 1 Newton of gold on the earth, and that's because 1 Newton of gold on the moon has a larger mass than 1 Newton of gold on the earth. And so let's actually calculate what the masses will be. So calculate the mass of 1 Newton of gold on the moon. And then the next question after that will be calculate the mass of 1 Newton of gold on the earth. So for now, let's do it for the moon. I'm going to go to Top Hat here. Yeah, the timer. All right, let me add maybe another 15 seconds. All right, let's see what we got. Did anyone need more time? If so, let's see, there's something in the chat. Sorry, there was a comment in the chat that I totally missed. Value is the same because the value is based on the mass, not the, yeah. Yeah, to the comment in the chat from the earlier discussion, the value is the same for the previous question because the cost is based on the mass, not the weight. So that is correct. The cost of it is based on the mass, not the weight. But the problem was that in the problem, they give you the weight and not the mass. And so therefore you have to convert back. All right, let's see. Okay, so I think it's, yeah, so I have like a 1% or 5% tolerance on the correctness of the answer. So I think the correct answer is indeed, what is the exact number? Is it like 0.6? 0.617? Yeah, so 0.617 kilograms is what weighs 1 Newton on the moon. Now let's repeat that calculation for what does 1 Newton of gold weigh? Sorry, what does 1 Newton of gold in mass in kilograms on the Earth? So let's see if you guys can figure that one out. 5 seconds, or maybe let me add 15 seconds. Okay, let's see what we have. All right, and I think the correct answer, what was the exact answer? Say again? 0.102 kilograms. That's correct. Yeah, so it looks like most of you got it. Uh,
Do those calculations, it's gonna come out in kilograms first. You don't need to-
yeah, it's literally this calculation right here. So on the Earth, the mass of 1 Newton is 1 Newton divided by the g of the Earth, which is 9.8 meter. So it's 1 divided by 9.8, and on the Moon it is 1 divided by 1.62. And to answer your question, this thing here has units of newtons over meters per second squared, right? That's what the units are. It has units of newtons divided by meters per second squared, right? Newtons divided by meters per second squared, and you can see that that is, what is a Newton? It's a force. Force is equal to mass times acceleration, Newton's second law. So 1 Newton is 1 kilogram times 1 meter per second squared, which is acceleration. All of that divided by meters per second squared. And so you see that the meter per second squared cancels, and indeed it has units of kilograms. Say again? Oh, right. This way. Why is this not? Oh, this is delay. Okay. Yeah. Right. So you see explicitly there that newtons per meter per second squared is really just kilograms. And so when you do 1 divided by 9.8, that is 0.102. When you do 1 divided by 1.62, that is 0.617. And therefore, hopefully that clarifies things. Any questions about that? So the moral of the story here is weight is different from mass. Weight is the gravitational force acting on you, whereas mass is the amount of stuff that is there. Okay. And finally, we have talked about Newton's first law, Newton's second law. We introduced the universal law of gravitation. We now come to the final thing, which is Newton's third law. These are all the postulates of Newtonian mechanics plus gravity, and then we work out the consequences of this in the rest of the course. So Newton's third law says that if object 1 and object 2 interact, the force exerted by object 1 on object 2 is equal and opposite in direction to the force exerted by 2 on 1. So that's a lot of words, and here's a diagrammatic way of saying this. So Newton's third law is true not just for gravity, but for any kind of force you may be talking about. It says, if I have two of these objects, object 1 and object 2, then if they are interacting with each other in some way, maybe they're exerting a gravitational force on each other. Maybe they're tied together by a string and they're pulling on each other through the string or something like that. Whatever the mechanism is, F12 here denotes the force that 1 exerts on 2. So here's object 1. It's exerting some force on 2. If it is in this direction, then the force that 2 exerts on 1 will be the same in magnitude, but exactly opposite in direction. Again, in Newtonian mechanics, there is no proof of this. It is simply an observation that if one object is exerting a force on another object, that other object will exert an equal and opposite force on the first object.
Touching each other, or just in terms of gravity?
in any situation. So even if they're interacting gravitationally, they will exert the same gravitational force on each other. Right? When you hit your hand on the wall, you're exerting some force on the wall is exerting the same force on your hand, which is why when you hit the wall harder, it hurts more because the wall is then exerting the same amount of force back at you.
But then what about when you move stuff? Aren't you exerting greater force?
That is a deep question that ties into some of my top hat questions that are coming in. So yes, let's actually explore that question. Let's see, is it the next one? Another way of saying this is that there isn't a single isolated force. Forces always exist in pairs. So if something is exerting a force on something else will exert a force on the first thing again. So there's always this pairwise connection. And notice that these force pairs, according to Newton's third law, they act on different objects. That is, F12 is the force that one exerts on two, but F21 is the force that two exerts on one. Right? Maybe take a swig of coffee to process that. You're literally doing that. Okay, awesome. So let me see if I have. Okay, yeah, I think I have some top hat questions on this. Let me. You already did this question, right? Okay. So this ties with the question that was asked here earlier. So again, this is a conceptual question. It says, consider a freely falling object of mass 5 kilograms. So a 5 kilogram object is just falling towards the earth. The question is, the statement is that the earth exerts a bigger gravitational force on this 5 kilogram object that's falling than the 5 kilogram object is exerting on the earth. Is this true or is this false? That is the question. So let me just go ahead and think about Newton's third law. Also think about the law of gravity. They're both helpful to think about. Five seconds. Okay, let's see what we have. Ooh, all right. Anyone want to defend their answer?
Gravity, say the mass of the object times gravitational constant over the radius of the object squared, divided. So,
Well, it's the distance between the objects squared. Yeah. Oh, I see. You're thinking about the Earth. That's right. Yeah. Go ahead. Continue.
so you get a much larger gravitational force from the Earth than you will a 5 kilogram object.
Anyone want to make the counter argument? So someone made the argument for true, that the Earth does indeed exert a larger force on the 5 kilogram mass than the 5 kilogram mass exerts on the Earth. Let me check. Well, what does Newton's third law say?
The force exerted by one object onto another is equal in magnitude, but they're in opposite directions.
Okay. Based on that, do you have a, what did you mark, A or B?
I marked B.
You mark B. So according to Newton's third law, you say that it is indeed B. So there's a comment in the chat. Whoops, sorry. The forces exerted are the same. The difference is the acceleration and the mass of each object. That is indeed correct. So let's this last comment actually goes into my next question. So the correct answer is indeed false. And let me just take a moment to address. So one answer that the reason it was false, that is the 5 kilogram object and the Earth are both exerting the same equal and opposite force on each other, just because that's Newton's third law. If the Earth is exerting a force on the 5 kilogram object, the 5 kilogram object has to exert equal and opposite force on the Earth. Now, someone was thinking about this in terms of Newton's law of gravitation. Notice that the force of gravity between two objects is G m1 m2 over r squared. You can see here also that the force that the Earth exerts on the 5 kilogram object will be G times the mass of the Earth times the mass of the 5 kilogram object divided by the distance between them squared, in this case, like roughly the radius of the Earth squared. But you can ask the other question, what is the force that the 5 kilogram mass exerts on the Earth? It's also G times the product of the two masses, mass of the Earth times mass of the 5 kilogram object, divided by the distance between them squared, which is again roughly the radius of the Earth squared. So you see that Newton's law of gravitation is consistent with Newton's third law. Otherwise, there would be a problem. And now comes the next question, which was kind of alluded to in this last comment on Zoom. So let's see the following. Consider a freely falling object of mass 5 kilograms, same thing again. The acceleration of the object has a greater magnitude than the acceleration of the Earth. Is this statement true or false? So let's think about that. And I'll give you a hint. Think about Newton's second law. Newton's second law has to do with acceleration. And see if you can figure this question out. Twenty seconds. Five seconds. All right, let's see what we have. The correct answer is indeed true. And this is the amazing thing. I'll leave you with this thought before you leave, which is that you are exerting the exact same force on the entire planet Earth that the planet Earth is exerting on you, except that you have a tiny mass compared to the Earth. The acceleration by Newton's second law is given by the net force over your mass. And so both of you are exerting the same force on each other. So this is the same. The mass of the Earth is 6 times 10 to the 24 kilograms. So it has a tiny acceleration, whereas you have a much smaller mass, you have a bigger acceleration. So actually, when you are falling towards the Earth is falling a little bit upwards towards you. except that its acceleration is really, really tiny, so it doesn't appear as if it's moving. But it is, just a little bit. All right, with that, I will leave you guys, and I'll see you on Wednesday.